Welcome to the second edition of 5G Academy at University of Naples Federico II. This is Team 4, and we are here to present you 5GRID, our project to install a 5G-enabled smart microgrid in a hospital. This is our team, a group of students with different backgrounds gathered together to put 5G at the service of our project. To start off, here is our agenda. The first chapter is an overview of the project, with the use case definition, so what is a microgrid and why the choice of a hospital campus as our use case, and of course benefits and profits of the use case. Second chapter is a more technical one, smart grid and 5G, the link between them and the innovative impact of 5G, general architecture, indoor-outdoor network NPN, and of course the experiments we carried out during these months, so MATLAB models and results. Third chapter is dedicated to the other pillars of this project, so security, business and regulation requirements, with a specific focus on the digital platform we elaborated. First things first, what is a smart microgrid? A microgrid is an independent power network that is able to meet local electricity needs through the use of local distributed energy resources. When software enabled, it becomes a smart microgrid. So through the use of softwares and intelligent controls, it is able to manage electricity in the most efficient way. The most challenging aspect about a microgrid is due to uncertainty, in particular, of the large number of small generation stations and the energy consumptions at the end user level that are generally fluctuating. As already mentioned, the choice of a hospital as our use case is due to the high energy demand of such a structure. A hospital is working constantly, performing critical and energy-intensive activities for thousands of patients every day, and taking care of not only life support systems, emergency rooms, and vital activities, but also food, laundry, sterilization, and of course, servers activities. As a result, the choice to implement a 5G-enabled smart microgrid in a hospital will show its best advantages. First of all, it will mean savings for the national health system or the private hospital that decides to implement such a project. So there will be business strategic goals such as reliability, affordability, sustainability that will be further analyzed during this presentation. Of course, it will mean reduction in costs of energy and optimization of energy resources, as well as enablement of new product services in reason of the fact that the energy surplus that will derive from this project will be stored and sold via columns used for the recharge of electric vehicles. Second significant aspect is sustainability. Our project will be entirely powered by renewable energies, in particular photovoltaic panels installed in the hospital campus, that will mean reduction of the greenhouse gases and other emissions and minimum power leakage. Third aspect is reliability of the system. Of course, it will have an enhanced capacity to meet the needs of the expected increasing demand of the public health services in future years. It will be a more resilient system, particularly due to the use of 5G solutions that allow better scalability compared to wired solutions. So even in case of enhancement of this project, the system will be able to meet the energy needs of the hospital. Last but not least, actually the very point of this project, is to grant the hospital independence from the national electric grid and uninterrupted energy supply in case of outage.
In a microgrid, we use 5G in 3 different sectors. We use enhanced mobile broadband to manage the national smart grid, because in the future the whole data about smart meters will send with 5G, and it is better use a NIC standard. We use ultra-reliable low-latency communication to connect the controllers, and we use a massive type communication to connect a lot of sensors and smart meters. To understand which communication types we need, we analyze the communication requirements between the different controllers. The control architecture is defined 3 levels: primary, secondary, and tertiary, and we use them to administrate the quality of energy. In the tertiary level, we have a microgrid energy management system. It involves non-critical tasks required for the power flow optimization in the microgrid. In the second level, we have a great impact on microgrid control performance because this controller is more sensible by high latency and packet loss. In the primary level, we have a control for distributed generator. In our case, we have photovoltaic panels, and it is a communication-less level because we have a time-critical control in it. In particular, we studied the secondary control exactly to the communication requirements that we evaluated, and we found in some different papers several comparisons with different types of communication. And the conclusion of this paper is that wireless communication was the best, because it is scalability, so we can modify the control architecture or improve it without to need to put other cables that are more expensive. So why not the Wi-Fi? We can think that it is better resolution because it is cheaper than 5G, but user license frequency for this is subject to more interference and more sensible to Gemini attack. How we can see in this experiment found in communication requirements and microgrid a particular survey paper, if there is a continuous perturbation in communication Wi-Fi, and we almost complete packet loss, and the second level cannot restore the reference value for the frequency. After, my colleague will talk about the analysis that we did in the second control respect latency requirements. Following the analysis requirements, we designed the architecture. In a general architecture, we have a radio access network to connect the smart meters and sensors and secondary and tertiary controllers. The energy management system runs with control software such as SCADA, which is executed in the edge control, which is within the hospital perimeter. In this way, the software can react quickly if there is any needs. Then some data that we collect are sent to a central cloud for the further elaboration, or to remote monitoring, or to view consumption data that we show in the app. Inside the building, we have a lot of sensors, like a temperature sensor, humidity sensor, sensor for UPS control, or to air quality control. Then we have an energy meter to measurement the voltage and the frequency. And then we have some smart switch, for example, to turn on or turn off the air conditioning in a court. We can connect this sensor with external, with fixed wireless access. We can use the outer receiver or indoor gateway. It depends by the niche that we external work case. Inside the building, to have coverage in all angles where is needed, we can put some relays. Naturally, when you want to implement inside connectivity, we should study the propagation with a specific program.
Regarding the outside, we will need motion sensors in order to know where people is, energy quality control to manage power, frequency and so on, smart meters to monitor active and reactive power flow, and also we have the communication between secondary and tertiary control layers. To provide 5G all around our hospital campus, we will need an integrated access backhauling, or IAB. IAB extends coverage using same 5G spectrum for access and backhaul. Technically, IAB works through time slot division. The distributed unit serves the local user during some time slots, and the IAB child during others, as you can see from the bottom right image. In other words, IAB works like a walkie-talkie. When one talks, the other keeps silence. In our microgrid, we will use a non-public network. Public and non-public network will use the same physical infrastructure, and the segregation between them is gotten by using different network slices. But why NPN? NPN prevents our data from going out of the hospital perimeter. This enhances security for two reasons. We can easily protect both the data and the edge control, to which we can provide energy if outages of the national grid happen. Lastly, we elaborated a MATLAB Simulink model to see how the network performance affects the quality of the control. On the left, you can see the Simulink model. The circuit is made up of two generators, which are photovoltaic panel in our case, interconnected among them and to the load with actual power lines, and so with their own resistance, capacitance and inductance. The green block on the left is the secondary layer of the controller. As you can see clearly from the image in the right, the input of the controller are the actual power provided, P1 and P2, and the frequency by each generator. We put delay, the zeta blocks, in the links in the input and the output in order to see what happens with different time delays. The goals of the controller are two. Keep the frequency stable at the nominal value of 50 Hz and to have load balancing. That means all generators provide the same amount of power even if something happens as a new load turned on, which is what happens in our simulations. We made two simulations, a 4G-like simulation with 10 milliseconds delay and a 5G-like simulation with 1 millisecond delay. The upper curves you are seeing are the frequency of each generator in time, while the lower curves are the active power provided by each generator. As you can see from the animation, the frequency is far to be stable, and also we don't have load balancing in the 4G-like simulation. In the second animation, extracted from 5G-like simulation, the frequency is stable at 50 Hz, and also we have power balancing, showing us how 5G can really make the difference when it comes to control in a microgrid. Now I leave the word to my colleague Roja, who will talk about security and digital platform in our project.
So I'm here to explain the security requirements of our project. So first we look at why security is important in healthcare. Data security is essential in healthcare industry because a lot of data about the patients that join in the hospital is being managed all the time, like 24/7 and 365 days. So there is a possibility of cyber attacks that can happen um, at this level of data storage in a hospital. So the main point here, looking at security of healthcare, is that when some attacks happen, cyber attacks happen at any other industry level, it could loss, it could lead to some financial loss, right? But when it happens to healthcare industry, it it leads to death of a person too, because cyber attacks can happen even to the devices used in the hospital. So we have to be more careful when it comes to security in healthcare. And now let us explain about the some of the data breaches that have happened in the last year, that is 2020, in USA, in order to better understand why security is important. So here in US alone last year there were 600 healthcare data breaches. So which is around 55% jump compared to 2019, the previous year of 2020. So it shows us the rate how much it is needed and important. Also the average cost has increased last year per every data breach that has happened, and the overall people affected from all these data breaches just alone in US is about 26 million people, which is not at all a small thing. Now let us explain why a secured microgrid is important in a hospital. So in order to build a secured microgrid, we have to follow some of the security objectives and the requirements. Like we have to fulfill some of the security objectives and requirements. The first main objective of any smart security related smart grid is about CIA, confidentiality, integrity, availability triad, and the requirements could be many, and we can limit them according to the usage. And some of them could be like authentication, authenticity, authorization, privacy, survivability, safety criticality, etc. So after meeting all the security objects and requirements, let us look at some of the secure practices that have to be followed. So in order to ensure the safety against the attacks that could happen at the microgrid level of the hospital. So, in order to ensure safety, we have to follow authentication, encryption, data privacy policy, updating of software, password usage, continuous risk management, etc. These are some of the examples that could be followed in order to achieve safety at different layers of the security of. Now, looking at threat identification and its impacts is one of the major thing that we have to look at when talking about cyber attacks, because it happens because of various vulnerabilities present at the system level and the network level. So it could impact us in two different ways, in economic way and in the fiscal way. So economic impacts would cause us a financial uh, loss, as well as we cannot give the appropriate forecasting. So in this way our market could go down and could lead to financial or economic losses. And in the physical way, we can it can impact the cyber attack happen because of various threats and vulnerabilities. It could impact on the voltage management on the microgrid, energy management systems that are installed on the microgrid. So in this way we cannot predict exact way of producing energy and managing it properly. Now, let us look at some of the possible attacks that could happen in our project. Okay, we have divided the attacks in three different categories, like the IoT devices that have been installed at the hospital level, with the app that we created for the usage of our management of energy supply, and with the cloud level where we store our database. So, with the IoT, some of the possible attacks are hijacking IoT devices, eavesdropping, botnet attacks, etc. And with the application level, we can say that injection attacks, SQL attacks, XSS attacks, man in the middle, etc. And with the cloud, we can say that hijacking of attacks, denial of service attacks, malware injection, etc. As I said, for the digital platform, we created an app where we can use everything using our app. We can get any information using our app. So, first, why is it required, or what is it used for? We can get statistics of the energy consumed in order to save the cost. We can get information about energy produced by panels and stored in battery systems or UPS. Also, we can check for the sensor information that we have installed at the hospital level, and we can also check for the monthly bills at various levels, like in the for a week or for 15 days for a month. And also we can check for energy availability at charging points where we charge our vehicles like ambulances, etc. And this app usage is restricted for security reasons, and only the engineers of our ESCO company and the hospital and the high level people like chairman or someone can only use the app. And this app is secured because only some people have can use it. Also, they can use it only with the credentials that our ESCO company provides them with. And when the credential with in one device is open, they cannot open the app with the same credentials in another device. This way we provided security in order to provide a safe and healthy environment to the people, to the customers.
In the next slide, we will see our business model, but before it is important to clarify some details. My team and I talked about microgrids in a generic way, but there are two types of it, on-grid and off-grid microgrid. Basically, the difference is the presence or not of connection to the national electricity grid. An on-grid microgrid is connected to the national electricity grid and it's completely autonomous system, while an off-grid system, also known as an island system, is completely disconnected from the grid. Basically, the second one is chosen in a specific environmental places in which there are not the presence of a national electricity grid. This is the reason why we opted for an on-grid microgrid for our business case. Another important thing is to differentiate the management system of the microgrid. As you can see, it is possible to choose between the microgrid as a service model and the customer owner system. The latter allows the client to own the microgrid. In this case, the customer pays a developer's costs, taking all the financial risk of the project. Our energy service company adopts the former, the as a service model, that allow more flexibility and less risks to our clients, ensuring certain and predictable payments. This type of grid management allows the hospital to own a microgrid without paying the upfront cost of installation. Now, let's examine how an ESCO works, paying attention to several phases. The first one, the audit phase, detects the state of production, processing, and use of the energy in the customer's building. Moreover, this phase allows to determine inefficiency of process in order to propose several alternatives to save money and energy. The benchmarking and verification of saving is the monitoring activity that allows to detect correctly the total cost of the microgrid implementation. Financial instruments are necessary to guarantee the realization of the project. In fact, the ESCO needs capital for the construction and management of plants. To ensure transparency of relation between ESCO and customer, it is necessary to create a complex contractual system, defined in the most detailed way possible. The energy performance contract is the contractual model that actually characterizes the activity of the energy service companies. The contractual relationship normally involves two parties, the beneficiary and the supplier, who usually anticipate the costs of the investment necessary for the intervention to be carried out in any case, undertake the obligation to find the financial means from third parties. The energy performance intervention can create different types of models of energy performance contracts. In our case, we hypothesized the shared saving, in which only a part of the savings contributes to the recovery of the investment. Now, what is necessary to create a smart microgrid into a hospital? There are several components to consider, and it is necessary to conduct a specific analysis to detect the precise cost for each client. That's why we below indicate a price range for each component, but it really depends on every single case study.
Among the risks identified, we have on the part of ESCO the construction and availability risk linked to the contractual achievement performance, on the part of the customer the demand risk relative to the availability of the subject customer to the fruition of the work in contractual terms, and on the part of the lender the financial risk relating to the economic validity of the transaction and the client subject, whose assessment shall be based on the identification and implementation of the main risk mitigation factors. That is, the assumption of the risk of a financier takes place at the evidence of the control of the main risk. As we can see from the figure, the risk trend follows three different phases of construction and installation of the microgrid, the initiation and full operation working. Risks are initially linked to the possible delays and unexpected cost. In later phases are possible changes in regulation and supply or market inflation, or risk linked by the performance and major forces. For the communication part, let's talk now about the creative process related to the brand realization and the corporate identity. Our logo wants to remember different aspects related to our project that, as we said before, is focused on the implementation of a smart microgrid in the hospital. So, the key elements that inspired us are the structure of a hospital, the energy battery and the storage. As we can see, the name is a union between the words 5G and grid, so 5Grid, which is the main element of our project, a tool for the distribution of electricity through the use of innovative technologies, such as 5G. The payoff that follows the logo contains the brand's mission, save energy, save lives. In fact, through an optimal energy management within a context such as a hospital, it is possible to obtain many benefits that impact the entire ecosystem.
For the regulatory part, we divided our work into a two-phases analysis. First of all, we asked ourselves what could be the regulatory constraints that could stop our business, and we figured out 3 different aspects to be taken into account. First, columns for electric vehicles that have not only physical constraints, but are also subject to some documentation to be presented for the public administration, not only for the whole project, in this case segnalazione certificata di inizio attività, but some additional local documentation for sanitary areas which are considered under constraint ones. Second aspect regards the electric implant of a hospital that has some distribution requirements, in particular for sanitary areas identified according to Norma CEI 710, and the compulsory backup energy supply for critical areas, which is demanded in a hospital. Third aspect is the relationship between smart grids and renewable energies. In 2013, the Trans-European Energy Infrastructure Act dictated law on smart grids and EU's policies objectives on renewable energies, and therefore has to be taken into consideration. Then there is a funding act, which is INEA agency, that uses the 77 billions from EU's Horizon 2020 project to fund smart grids and clean energy solutions. Third, recommendation and standardization roadmaps proposed by Smart Grids Task Force in 2009 is the basis on which to found our project. After that first analysis, we realized that the feasibility check of our project required much attention on some other regulatory aspects. First of all, public funding instruments. Therefore, we identified some EU funds like LIFE 2021-2027 for the energetic transition and some Italian funds like Fondo Nazionale di Efficienza Energetica and Titoli di Efficienza Energetica, so-called certificati bianchi. These are actual certificates that are emitted by the public administration according to the amount of energy saved by our project and are convertible into money. Therefore, they are an effective funding instrument, and both the Fondo Nazionale Efficienza Energetica and certificati bianchi can only be asked to the public administration via the use of an ESCO company, which is therefore essential for our project. Second aspect is the conformity of the hospital electric implant, so there are specific prescriptions for medical areas and requirements for the electric power plant, some security checks that have to periodically be performed, and of course the aspect of the compulsory backup energy supply for critical areas, which is the very point of this project. Columns for electric vehicles, so we made it possible for the ESCO company to sell the energy surplus to private users. The energy is actually purchased within the European Union, and the columns are accessible 24/7. Of course, we took care of all the documentation that had to be presented to the public administration of Italy.